Okay, this is characteristics of light. This is starting our new unit on electrons and electron configuration. So first, most people know and think of light as a wave, light waves. In fact, visible light we call electromagnetic radiation. Electromagnetic radiation is a wave, and true to its name, it means that it has an electric and a magnetic field. Okay? So light means that it carries an electric field, and it also carries a magnetic field. And some types of that is X-rays, ultraviolet, infrared, microwaves, just like a microwave oven. Radio waves, these are all types of electromagnetic radiation, and these are all types of light. So visible light is in the same family as X-rays, ultraviolet rays, and microwaves, and gamma rays, and all those good things. So together, all of these form the electromagnetic spectrum. And so here is an example of the electromagnetic spectrum. Okay, so the electromagnetic spectrum has everything from radio to microwave to infrared to visible, ultraviolet, X-ray, and then lastly, gamma rays. As you can see right here, it shows you about the wavelengths. So as you get farther and farther, the wavelengths get shorter and they get more and more squished until gamma ray where you have very short wavelengths. And then frequency, this bar shows you that visible light falls right here. So visible light, amongst all the light that you can have, visible light only falls in this area. And then blown up, you have everything from red, orange, yellow, green, blue, indigo, violet. Remember Roy G. Biv from middle school. So do a quick sketch of all of this in your notebook. You need to know the order from radio, microwave, infrared, visible, ultraviolet for the future. Okay? So all forms of electromagnetic radiation move at a constant speed. So X-rays go at the same speed as microwaves, which go at the same speed as visible light. And that is, of course, the speed of light, which is the letter c. And the value of that is 3 times 10 to the 8th meters per second. So that's 3 with 8 zeros, which is 671 million miles per hour. So speed of light is pretty fast. I mean, obviously when you flip on a light switch, light comes on instantly, to you at least, but it does in fact have a limit. So here are the parts of a wave, so parts of light. The first thing that we need to know is wavelength, which we will use the Greek letter lambda for, and lambda is this guy. He kind of looks like an L leaning against a stick. That's lambda. Okay, so we use that to denote wavelength, and wavelength is the distance between the same points on adjacent waves. So if you have one wave and you look at the distance between the same points, that means that is the wavelength. Okay, for light, the unit for wavelength that we use is most often nanometers, and a nanometer is 1 times 10 to the negative 9th meters. So it's the next step. You have normal meters, and then after centimeters and millimeters, we have micrometers, and then even smaller than a micrometer is a nanometer, and that's 1 times 10 to the negative 9. Okay? So here's a picture of a beach wave. So you have the waves kind of moving to the beach, and they hit a pier, a beam in the water. So again, the distance between one point and the exact same point on another wave is the wavelength, lambda. Okay? So then here's an example of a shorter wavelength, right? Smaller waves, and it goes from the same point to the same point on a different wave, and that is what wavelength is. Okay? So, using this picture again, what color has the longest wavelength? So you have red, green, purple. Using the diagram, tell me which one is the longest, which color is the longest wavelength, and which one has the shortest wavelength. Okay, so pause this recording, write down this question on the opposite side of your notes, and press play when you're done. Okay, so when you look up here, red over here the waves are separated out more over here. So the distance between crest and crest is higher on red. So red has the longest wavelength, okay? So on the shortest, when you look over at purple, purple has them the most squished and the crest to crest is the smallest. So the shortest wavelength is violet or purple. So continuing parts of a wave, the next topic we have is frequency. Frequency is denoted by F, the letter F, and sometimes you will see it as the Greek letter nu, which looks like a V, but it's nu. Okay, so frequency, just like if I said how frequent does something happen, it means how many times does it happen in a certain time period. So the frequency of a wave is the number of waves that pass by in a time period, in this case 1 second. So the units are called hertz, Hz. So 1 hertz equals 1 wave per second. So that means if a wave has a frequency of 1 hertz, in 1 second you will see 1 complete wave pass you. Okay? Now sometimes you might hear of internet connections or phone lines being a certain number of gigahertz or megahertz. That again just means that the waves that are going through that cable have a frequency of 40 gigahertz or 40 megahertz. Or even sound is often used that because sound is a wave. So you hear sound waves talked about in hertz a lot as well. Any kind of wave, the frequency is usually in hertz. Okay, so here's an example. The first wave has a high frequency, and the second wave on the bottom has a low frequency. And you can think about it. So let's say time passing, this is 1 second, is like right here. Okay, so that means in 1 second, 1, 2, 3, 4, 5 waves pass. So you would say this has a frequency of 5 hertz. Now on this one, in 1 second, just 1 wave passes. So this bottom one would have a frequency of 1 hertz. So for frequency, the more squished a wave is together, the higher the frequency. The more stretched out a wave is, the lower the frequency that wave is. So now we're going to get into how fast waves go. So wave speed. So the equation for the speed of light, and actually the equation for any speed of a wave, is c equals lambda f. Now of course for this case, for light, the velocity or the speed is always going to be c, or 3 times 10 to the 8th meters per second, the speed of light. But that's equal to the wavelength, lambda, times the frequency. So that means since this is always constant, if you know lambda, if you know the wavelength, you can find the frequency. Or if you know the frequency, you can always find the wavelength using algebra. Okay? So since c is always constant and we can find out the other two, we find that they are inversely proportional. And what that means is that when one is high, the other will flip and do the opposite thing. When you use their proportions, they're inverse. When one goes up, the other goes down. So when wavelength is high, frequency is low. Okay? You see they're inverse, they're inverted. They do the opposite. Okay? And then when the wavelength is low, or when the wavelength is small, the frequency then is going to be high. Okay? So, again, write that down, and then here's an example. Draw this on the other side of your notebook. Draw the first wave, and then draw the second wave. Shorter wavelength, longer wavelength. Now, I want you to guess which one has the higher frequency and which one has the lower frequency. So pause this video and do that right now. Okay, so the shorter wavelength, since they're inverse, is going to have the higher frequency because they're opposite. Short wavelength equals high frequency. And the bottom one has a longer wavelength, so it will have a lower frequency attached to that. Okay, so that's called inverse proportions. They're inverted from each other. They do the opposite thing. Okay, so the last thing we're going to talk about is the energy of a wave. So we've done wavelength, we've done frequency, we've done the speed, and now we're going to measure the energy of a wave. Okay, so wave energy for electromagnetic waves or light is found by E equals hf. Okay, E is energy, H is Planck's constant, and we're going to learn more about him in the future, but his constant, the number that's named after him, is 6.6 times 10 to the minus 34 joule seconds. Now you don't need to know what joule seconds is yet. That would be coming in the future, but the units are JS. And then F is frequency. So if you multiply the frequency of a wave times Planck's constant, you get the energy of that wave in joules. And joule is going to be a unit for energy, which we will learn soon. So when we look at these, remember that the top one has a shorter wavelength, which means a higher frequency. Therefore, it's going to have more energy than the bottom one. Because, remember from back here, energy is related to frequency. So the one that has the higher frequency will have the higher energy too. So this one has more energy than this one. Okay? Again, there's higher frequency, lower frequency. So, on Monday, we're going to learn about, why are we learning about light at all? I thought we were learning about electrons. So on Monday, we're going to do a wacky wave worksheet, kind of practicing some of the stuff that you learned in this video about waves and doing kind of more of those calculations about velocity and wavelength and speed and energy. And then after that, we're going to do our flame test lab. Okay, and then we're going to see that light and electrons actually have a lot to do with each other, and in fact is how we discovered that electrons move in orbitals, and everything we know about orbitals comes from practically the light that different atoms give off. So tune in Monday, take good notes on this, and I will see you then.